Okay, so I'm Jeffrey Uy and I will show you how to solve this problem using mathematical induction. Our first step is to show that it works for one number. But first, we show the expanded form of this equation. So it is 2 times 1 minus 1 plus 2 times 2 minus 1 plus 2 times 3 minus 1, and it goes on until 2 times n minus 1 equals n squared. So what we do first is we show that it works for one number. So we substitute n with 1. Proposition 1 is 2 times 1 minus 1 equals 1 squared. We can get 2 minus 1 equals 1 and 1 equals 1. So we can say that P1 is true. Our second step is we show that it works for all pk. So we can say that if Pn is true, then Pk is also true. So we assume that Pk plus 1 is also true. So Pk is simply 2 times 1 minus 1 plus 2 times 2 minus 1 plus 2 times 3 minus 1 plus on and on until you reach 2n minus 1 equals k squared. Since we assume that Pk plus 1 is true, we can say that Pk plus 1 is 2 times 1 minus 1 plus 2 times 2 minus 1 plus 2 times 3 minus 1 plus goes on until 2k plus 1, 2 times k plus 1 minus 1 equals k plus 1 squared. Since we can see that the first few terms of Pk plus 1 is equal to Pk, we can use the transitive property to substitute. So we can get k squared plus 2 times k plus 1 minus 1 equals k plus 1 squared. Now we prove it. So k squared plus distributing 2 to k plus 1, we will get 2k plus 2 then minus 1. Then squaring a binomial, first we square the first term, k squared, multiply by 2 both the first term and the second term, plus 2k, then square the last term, plus 1. So we can get k squared plus 2k plus 1 simplified equals k squared plus 2k plus 1. So we can say that it is true. So therefore, Pk plus 1 is true whenever Pk is true. And since P1 is true, then Pn is true for all elements of positive integers by the principle of Optical induction. Thank you.